Welcome everyone. I am so excited for today's video because today I have the pleasure of welcoming a very special guest here to the channel. He is the Department Chair of Mechanical Engineering and Materials Science and the Lee Hunter Distinguished Professor at the McKelvey School of Engineering in Washington University, St. Louis, Missouri. In 1996, he received the National Science Foundation Career Award, and in 2004, he was awarded Engineering Professor of the Year and has twice since received the School of Engineering and Applied Science Big Fish Award for graduate student mentoring. He works with magnetic resonance imaging, more commonly known as MRI, to investigate the mechanics of brain injury and brain development. And he is none other than Dr. Philip Bailey. Thank you so much for coming in today, Dr. Bailey. I cannot wait to get into our discussion.
Great. Thank you for having me.
Yeah, absolutely. So to begin, I would love if you would just share a little bit about your work, the work that you're doing, ongoing in your lab, any research, or any work that you've done in the past relating to traumatic brain injuries.
Yeah, I'm glad to talk about that. So I'm a mechanical engineer, and mechanical engineers understand the relationships between forces and motion. And of course, in traumatic brain injury, that's an example of a force being applied to someone's head and the head and the brain moving. Particularly, the brain deforms, and when brain tissue deforms quickly, it can get injured. So our role as mechanical engineers is to understand the process of impact, the forces that are applied to the head, the acceleration of the head that results, but most importantly, the deformation of the brain tissue that results. Specifically, our group has developed dynamic MRI imaging methods so that we can visualize the deformation of the brain in response to head motion, imposed skull motion. And so we're one of the few groups that has developed these techniques and then analyzed the data to experimentally measure how the human brain deforms during head impacts and imposed skull motion.
Okay, understood. So you're once you're able to figure out how the human brain it sort of deforms, do you apply that research to designing um, designing different technologies to better protect the brain?
Yeah, well, fundamentally, we're specialists. We make the measurements and we convey them to different people. The most important audience or customer for our work are people that build simulations. And we ourselves, we build simple simulations, but there are groups that specialize in building computer models and simulations of brain biomechanics. The measurements we make are all sub-injury level. They're very mild. They're less than someone would experience, for example, heading a soccer ball in a soccer game. And we know that because we started out measuring what people experience when they head a soccer ball in a soccer game. So we measure low amplitude impacts and the response of the brain to those sort of low level um, uh, excitations. The people who build computer simulations are interested in looking at potentially injurious impacts or blasts or bad things that can happen to the brain. So they're going to build what are called finite element models that basically take the brain and break it up into small elements of tissue and connect them together so that you can predict how this soft, complicated object deforms in response to the impact. It's the same type of simulation that someone would do if they wanted to, for example, simulate how an automobile would respond in a high-speed impact, or an airplane would respond as it's going through turbulence. Those are all analyzed by, these days by finite element models and computer simulations. So anyway, we provide our experimental data to the people that build those computer models. And then those computer models are used to develop safety methods, for example, for automobile manufacturers to develop football helmets or even other form or bicycle helmets or other forms. And to some extent, they're used to help people in the neuroscience, neurology, neurosurgery understand what's happening. But again, our primary direct customers are the people that are building these simulations, which are then used for a variety of purposes.
Okay, understood. And one last question relating to your work. So I understand that you use a method known as MR elastography to within the MRI imaging to investigate brain injury. Could you describe a little bit about how that works and
Yeah.
what you use it for?
Yes, absolutely. So MR elastography is a particular type of MRI, and if you've ever had an MRI, there's multiple MRIs you can have that depend on what the magnetic field and the radio frequency pulses in the scanner are. I mean, you're sitting there doing the same thing, usually lying still, but the scanner can do different things and discover different behavior of your brain. The blood flow, for example, or the uh, the different chemical composition of the tissue. We use methods that are sensitive to motion. We either apply large motion and watch the image change, or we apply very small motions and look at changes in the signal that detect motion. So what we're doing is in MR elastography, we're actually detecting shear waves, so waves that propagate through the tissue, very much like an earthquake. You may have heard of P waves and S waves. In an earthquake, S waves are the shear waves in which the motion is, if you see my finger, the motion is perpendicular to the direction of propagation. So anyway, we're looking at, you can think of earthquakes in your brain or shear waves in the brain, and from the shear waves, from the speed or wavelength of the shear waves, we can determine how stiff or elastic the tissue is. So what the elastic properties of the tissue are. So we're using MRI to measure the elastic properties of the tissue by watching shear waves go through the tissue, and that's called MR elastography. So what do we do with those properties? Again, we provide those properties to either people who want to simulate the brain's behavior, its response to an impact. You need to know how its mechanical properties for that. Or again, you can provide those properties to a medical professional or someone who wants to understand how healthy the brain is, and they might tell you something about the health of the brain.
Okay, understood. And actually, that brings me into another question that I had today is, are certain parts of the brain more susceptible? Because it sounds like the MR elastography allows you to figure out whether parts of the brain are more elastic or stiff. And is there a difference in the elasticity or stiffness of a part? And how does that affect its susceptibility to injury?
Great question. Absolutely. We know that the brain is not uniformly stiff, like a rubber ball, which has got, the same material throughout. It's got different materials inside. It's got white matter and gray matter. It's got membranes surrounding it and so on. It's got blood vessels inside it. Typically, for example, a blood vessel is stiffer than brain tissue. And within the brain tissue, white matter is typically a little bit stiffer than gray matter. And white matter, we have determined, this is one of our own research findings, that white matter is stiffer in one direction than another. And that's primarily because white matter is composed of neuronal fibers, fibers that connect one neuron to another. Those are actually, they're called axons. And our observations suggest that these axon fibers stiffen the tissue a little bit like a carbon fiber reinforced composite is stiffened or reinforced by the fibers. Anyway, yeah. So there are parts of the brain that are stiffer than others, and there are parts of the brain that seem more easily damaged. White matter, these fibers that connect cells, are a known source of injury. So those fibers can be torn or disrupted, and then that causes a degradation in people's ability to function.
Hmm. Okay. And okay, so if certain parts of the brain are more susceptible and you measure that, so are this how do you understand how are you able to figure out whether stiffer parts or more elastic parts are more susceptible?
Yeah, I mean, so mechanically, you can you can look at the motion of the brain and see which parts are deforming more than others. Those are things we can measure directly. Or you can take the simulations that people build and you can run those computer simulations and watch, for example, the entire uh, um, deformation of the brain under a simulated impact. Again, you may have seen animations of a car impact or a plane crash or something like that, and it's very analogous. You can see which parts are damaged in a particular impact, and of course those depend on the properties. Yeah, that's basically the recipe for answering those questions.
Okay.
I will say, I'll just add one thing, is that even though you can see the deformations, you may not be able to see the actual injury. It's possible that performance or function can be degraded without a visible injury. It's almost like you can have an invisible or a crack that's too small to detect, but it still changes the behavior.
mhm. Um, so intuitively, though, you would think that a more elastic part, even though it deforms more, since it's able to deform more, it can take like more brunt of force. Is that true, or is it just that stiffer parts of the brain are less susceptible in
Yeah,
general?
we don't know. It's a great question.
Okay.
As you say, and if it was purely mechanical, yes, something that's compliant like a rubber band could stretch a long time without it being, um, broken. And something that's very stiff, like a piece of paper, if you start stretching a piece of paper, it's going to break first. So their deformation is not indicative. But then you have to go the next step and understand the relationship of mechanics to biology or mechanobiology, and say, how does that axon respond to stretch? And axon, does it conduct the signal um, uh, that it used to conduct after it's been stretched? And that's again another downstream research area from ours.
Okay, yes. That makes sense. So now, along with talking about which parts of the brain are more susceptible, nowadays we're improving on various different technologies within helmets to protect the brain. But in general, what is your opinion on the effectiveness of helmets?
Yeah. So, I mean, clearly, from what we've seen in recent years on pathology labs who looked at postmortem of former professional football players, we're not preventing all the injuries. And if you've seen a football game or you've seen news stories about people coming back from combat, and that the current helmets that people use in combat or in let's say professional football or high school football or college football, they're not preventing all the damage. But I think it's fair to say that they have been somewhat effective in reducing it. But to go out and say we've improved the helmets, now it's safe to go, fall, be tackled and hit your head on the turf, that's definitely not the case. People are still being knocked out of games and being, you know, experiencing long-term injury, um, and experiencing deficits after uh, exposure to blast and things like that. So there's definitely, I guess you could look at it two ways. There's ideally room for improvement of helmet technology, or the other way to look at it is there's situations that are really hard to be protected from. If you're going to go collide with someone else at full speed, and bang heads with them, it's really hard to make that safe, completely.
Yeah. And so online, when you read about these kind of helmets, it's said a lot that helmets were only designed to protect from skull fractures, which I would say they do for the most part. But would you say it's safe to say that at this point, we don't have a helmet that's really even close to being fully concussion proof or
No,
TBI
that's
proof?
correct. We don't have a concussion proof helmet or a helmet that's proven to prevent the chronic traumatic injury that people have been experiencing. So those are still unsolved problems. But yes, you're right. There's very low incidence of skull fracture in helmeted sports.
Okay. And just moving in a slightly different direction from helmets, there's this new item that's come out known as the Q collar, which you may be familiar with. And for our audience, if you don't know what the Q collar is, it's a device that goes around your neck, and when you're in a collision, it tightens around the neck and sort of forces blood up into your head, tightening the brain and not allowing it to have as much space to move, filling up the blood vessels around the brain. it's sort of actually like what a bighorn sheep does when it goes into a collision. So do you think that that is an effective solution, or do you think it's not really scientifically backed?
I think it's the jury's out, and I think there's actually room to investigate that. Actually, using some of the techniques that we've developed. So, one of as you said, the premise is that by restricting blood flow, they actually are claiming or suggesting that the stiffness of the brain tissue is increased. The brain becomes sort of more turgid and pressurized, and is less likely to is going to deform less, as we talked about. And that's certainly something we can, or someone could investigate by performing MR elastography, measuring shear wave speed through the brain if someone's wearing a Q collar or not. So I think it's an open question. It's I can see the plausibility. There's also, I think you want to counter I mean, there may be potential risks in playing a sport or whatever experience you're having with your blood flow restricted in that way, and so you have to consider that too. I would guess, but again, we have not looked at that directly, and so I can't speak definitively with respect to its effectiveness.
Mhm. Okay. Um, and so along with helmets and the Q collar, I mean, we're improving the technology at a drastic rate, but in your opinion, what is really the best solution to preventing or reducing TBIs?
Yeah. So at this stage, the best solution is to minimize or regulate the amount of and severity of head impacts you're exposed to. So what that might look like in football is, limiting contact, full contact football until a later age, or even during the season in college or high school, having practices that focus on skill development and not full contact. So that certainly, plays a major role. I mean, if you can just do the math, most impacts, would occur in a week of practice as opposed to a game. So there is opportunity to reduce the overall cumulative load and opportunity for impacts in sports. In combat, I mean, obviously, um, training smart so you can perhaps simulate some sort of combat situation without full exposure to the blast or impact. Those are the things I'd suggest. In soccer, for example, there's a lot of soccer you can play before you begin heading, and I will be the first to say that heading in soccer is a order of magnitude thereabouts less than the impact you'll see in football, but it also has the opportunity to for head-to-head combat or compact impact or impact with the goalpost around. So basically, the best strategy is to minimize the number and severity of impacts, and then helmets are really a second level thing.
Yeah. So really the best solution is to avoid contact, which is of course the most intuitive thing to do. So, okay. And really just to wrap up, are there any final thoughts that you have about anything that we've discussed today, or where do you think that the field of TBI prevention and brain injury investigation is headed?
Yeah. Well, there's a couple of important things. One of the things I want to emphasize is that the importance of having experimental data to evaluate computer simulations. That's something, again, that's our role in this whole effort. And I think it's really important because it turns out that it's not that difficult to build a computer model of the brain, but in this case, it's actually really hard to know if that computer model is any good, because it's hard to look inside someone's head and see their brain move. So I think the thing of the development of methods to evaluate and build confidence in computer simulations is a really important thing in any engineering or scientific endeavor, especially in this day and age when you can simulate a lot of things or use AI to predict a lot of things.
Yeah.
I really think the importance of checking and assessing accuracy of predictions is really important. within brain injury, we have one thing that's intriguing from our own lab is we've determined that the brain has some natural frequencies, some frequencies that it likes to respond at, like a bell or a piano string or a guitar string. You hit a piano string, right? It resonates at a certain note, and it's going to respond to that excitation as well. And if you can somehow maybe avoid the frequencies that it likes to respond at, maybe that has an opportunity for deadening or reducing, especially people that are exposed to again, something like artillery fire or something that's what it's coming in at, and you have few options to avoid it. So anyway, the natural frequencies of the brain, the natural modes of vibration of the brain are kind of an interesting topic to us. The other thing is it's becoming easier and easier to get sensors, small sensors, to measure the motion of the brain. So it's really exciting to see what people can learn from those. Again, you want to make sure that you're actually making good measurements, because it's also possible to pick up noise or get some erroneous information if your sensors aren't good. But the development of new sensors to measure head motion in sports is good.
Yeah, definitely. And do you think things like electroencephalograms and other technologies like that could be useful in that endeavor?
Yeah, as imaging becomes more accessible, and measurements that don't require even expensive medical scanners, those pieces of information, those measurements, I think will be valuable in assessing, giving insight into injury. Right now, I think most medical professionals will make their evaluation of concussion or damage based on pretty subjective criteria. Can you count backwards, or walk a straight line, or things like that. So better assessment measures are exciting area of research.
Yeah, definitely. All right. Thank you so much, Dr. Bailey. That's all the questions that I have. It's really been outstanding having you here today. I really appreciate you coming in, because knowing how busy you are, it really, really means a lot that you were able to come in and give your expertise and your insights into this incredibly important field of TBIs and TBI prevention.
Great. Well, thanks for having me. And you've got some great questions, and I hope your audience finds this of interest.
Yeah, definitely. I know I learned a lot, and I'm sure they're going to enjoy listening to you and hearing from you. So thank you so much again.
Another huge thank you to Dr. Bailey for coming in today and giving us his thoughts on, again, this super, super, super important field of traumatic brain injuries and their prevention. Everything from the work he does in his lab, to the methods that he uses, to whether he thinks that helmets and other upcoming protective technologies are effective. All of that is so important and so meaningful to hear from an expert and a leader in the field of traumatic brain injuries and mechanical engineering like himself. So a huge, huge thank you to Dr. Bailey for sparing his time in such a busy schedule to come in and give us his insights today. My biggest takeaway from today's conversation with Dr. Bailey is twofold. First, we need to continue to strive to develop better protective technologies for athletes to keep them and their brains safe at all times, whether that's implementing new technologies into helmets or finding new innovative ways to protect athletes, such as the Q collar that we discussed earlier today. And second, advocacy for decreased contact in youth sports is imperative. It is crucial that young athletes focus more on skill development and less on contact, and save the contact for their professional career so as to not damage their brain too much at an early age, especially before it's fully developed. With all that being said, I would love if you all would throw your comments, takeaways, questions, answers to questions you have from today, such as whether you think helmets are effective or whether you think certain parts of the brain are more susceptible. Throw all of that in the comments below. That's it for today. Smash that like button. Hit that subscribe button if you haven't already. This is Vihan signing off. Have a great rest of your day.